Hello, and welcome to a video tutorial on Math 250, Section 6.5, Orthogonal Matrices. In our tutorial, we will go over what an orthogonal matrix is, how to identify whether or not matrices are orthogonal, some of the properties of orthogonal matrices, and we'll conclude with a short proof that involves orthogonal matrix properties. By definition, an orthogonal matrix is a square matrix whose columns form an orthonormal basis for Rn. To verify that a square matrix is orthogonal, we do have a couple of options. For the first example, I'm going to show that the columns are distinct and form an orthonormal set. For our first example, I will bring back one of our favorite matrices in the course, and that is our rotation matrix, cosine theta, negative sine theta, and cosine theta. So what we'd like to do here is show that the columns are indeed distinct and form an orthonormal set. So to begin that process, we are going to look individually at each column and take a look at some dot products. So we're going to first look at cosine theta, sine theta as its own column, and then negative sine theta, cosine theta as its own column vector. And if we find the dot product, recall that we multiply first entries together. That will give us cosine theta times negative sine theta. And then we add to it the product of the terms in the second row, sine theta times cosine theta. And we notice that these are opposites. I have a positive sine theta cosine theta, and then I have a negative sine theta cosine theta. That gives us a dot product of 0. Also, if we multiply each column by itself, to take a look at norm, I have cosine theta sine theta times cosine theta sine theta. If I find that dot product, I get cosine squared theta plus sine squared theta, which we know by identity is 1. And if I repeat it for the second column, if I multiply it by itself, negative sine theta cosine theta times negative sine theta cosine theta, I get a very similar result. I get sine squared theta plus cosine squared theta. And that also adds up to 1 by identity. So based on this information, we have that the columns form an orthonormal set of two distinct vectors in R2, this being the first, and then this first column being the first, and the second column being the second. So therefore, treated as a whole matrix, we classify it as orthogonal. It turns out that there are a number of other ways we can arrive at the same result. Theorem 6.9 is one of those theorems that gives us equivalent statements. If we have a square matrix, again, pay attention to the minor details. If we have a square matrix Q, saying a matrix is orthogonal is equivalent to any of these other 4 properties, and they all imply one another. I would say that the most common property that we use to mean the same thing as being orthogonal is the second one, that the matrix transpose times the matrix is equal to the identity matrix. That's the best way to show whether or not a matrix is orthogonal. There's a couple of other properties. If the matrix Q is invertible, then its transpose is equal to its inverse. Q preserves dot products for any vectors u and v, and then Q preserves norms for any vector u in Rn. The last two are less common. I would say B and C are a little bit more common. So to show you an example, if I take a look at this first matrix here, it's a 2 by 2 matrix. That's good. We're working with a square matrix. I want to determine whether or not the matrix is orthogonal. So to do it, I would like to use property B. Is Q transpose times Q equal to the identity matrix? So I will call this matrix Q. Therefore, the transpose would be when the rows become columns, so that turns into 0.7, 0.3, negative 0.3, and 0.7. If I then multiply Q transpose by Q, using the row by column approach, I notice that when I do row 1 times column 1, that's 0.7 times 0.7, so we have 0.49, and then plus 0.09. That adds up to 0.58. That's not good. So if we continue, just for completeness sake, for the next entry, I'd have 0.21 minus 0.21. We got a 0. 0.21 minus 0.21, another 0. And then in the last entry, 0.9 plus 0.49, that's 0.58. So while it does look like the identity matrix a little bit with the placement of the zeros, unfortunately, it is not equal to the identity matrix with our entries of 1 and the standard vectors serving as columns. So therefore, this matrix is not orthogonal. For the second matrix, we notice an interesting arrangement of numbers. We got some zeros scattered about. We have some ones. We have a coefficient in the front. So not to worry, this is not as terrible as it looks. So just like before, we will call this matrix Q. The transpose of matrix Q allows me to keep that coefficient in the front still. That'll stay out there, but the entries inside will just move around a little bit. So inside, again, our rows become columns. And we notice that not much changes. We notice that the matrix we get out is exactly the same one as what we started with. So if I now go and multiply those together, Q transpose is that. And I'm going to multiply it by Q. Just to keep things simple, I'll take care of the 1 over radical 2 times 1 over radical 2. That's just a half. Those are scalars, so we can get that out of the way. And then when I start to do row by column in the 3 by 3s, I would do the whole first row by the whole first column. That adds up to 2, 1 plus 0 plus 1. In the next entry, I would have 0, 0, and 0. In the next entry, I have 1, 0, and negative 1. That adds up to 0. For row 2, I take this row here and then I'll multiply it by each column. So that would give me out 0, 2, and 0, 0, 0. Lots of zeros. And then in the last row, I have 0, another 0, and 2. So for our final step, if we just multiply each term inside by that 1/2, I'm taking half of each of those diagonal entries, and lo and behold, we get out the identity matrix for the 3 by 3 matrix. So this indeed would be orthogonal since we got out the identity matrix. So property B definitely is the best one to use. Again, you can choose to use C if you want, but that would require finding inverses, and that's a lot of work, especially for the 3 by 3. So I would stick to property B. A nice convenient way to tell whether or not a matrix is orthogonal. For the next part of our lesson, we will take a look at some properties of orthogonal matrices. Now that we know how to prove whether or not a matrix is orthogonal, what types of things can we learn about orthogonal matrices? So the first interesting fact is that the determinant of an orthogonal matrix is either positive or negative 1. We saw from earlier that our rotation matrix was an orthogonal matrix, and we already know from previous work that that has a determinant of positive 1. But generally speaking, this would always be the case. Just to give you some intuition, we know that if a matrix Q is orthogonal, then Q transpose times Q equals the identity matrix. So if I work my way backwards, if I start with 1 as the answer, I know that that already is the determinant of any identity matrix, which is a square matrix. Then I can replace the identity matrix with the product of Q transpose times Q, and that goes back to property B from before. And then using our determinant properties from chapter 3, I can rewrite this as determinant of Q transpose times determinant of Q. Next, we can swap out determinant of Q transpose with just determinant of Q. As we saw in the last example, the transpose is the same as the original. So that simplifies to determinant of Q squared. And if you look at this as starting with 1 and ending with determinant of Q squared, we've maintained equality at every single step. So now we can just join the first step and the last step together. And the only values that square to be 1 are positive 1 or negative 1. So that just gives you some reasoning and intuition as to why we have that result. And we can follow similar proofs for B, C, and D. They're all located in your textbook if you wish to check them out. But I thought that this proof exercised some earlier concepts in an interesting way. Let's take a look at some true or false questions. So the first question is an if-then statement. If P is an orthogonal matrix, then P transpose is an orthogonal matrix. Take a moment just to stop and think. Do you think that would be a true statement or a false statement? And hopefully you've thought about it for a couple seconds. This indeed is a true statement. If you have a matrix that's orthogonal off the bat, then its transpose will also be an orthogonal matrix for reasons we discussed here on this slide and also over here in this example. True or false, if P and Q are individually orthogonal matrices, then their sum is an orthogonal matrix. So think back to what we've discussed in this course about adding matrices and multiplying matrices and whether or not properties carried over when that happens. So take a few seconds to think about it. And the answer to this one, I hope you got correct, was false. Adding two orthogonal matrices up likely will not preserve a lot of the properties we discussed. And a great example could be, we talked earlier in the course about using ones and zeros and identity matrices to prove things wrong. So if we chose the positive identity matrix for P and the negative identity matrix for Q, 2 by 2, each of these individually is orthogonal, but if I add them together, that's a zero matrix. And we know the zero matrix doesn't have a determinant of 1, among other things that are equivalent to these steps. So for that reason, that is a false statement. And then the last statement, true or false, every orthogonal matrix is invertible. Think about that for a moment. Okay, so when we talked about invertibility back in chapter 2, one of the requirements there was that we had a non-zero determinant. Because an orthogonal matrix has a determinant that is non-zero, it's either going to be negative 1 or 1, then we can be sure that if we have an orthogonal matrix, it will be invertible. So the answer to this one is true. For our last problem, we're going to do a little proof. We're going to take these matrices A and B. We're going to assume that they are orthogonal matrices, and we would like to show that their product, BA, is also orthogonal. So the key to doing a proof like this is to go back to the same theorem we've been using all along, theorem 6.9, and you will find property B once again to be really, really helpful. So we are going to just recall that in general, if a matrix is orthogonal, that Q transpose times Q is equal to the identity matrix. So in our case, what we would like to show, these are just some ideas before we get going. We would like to show that if BA is RQ, we would like to show that BA transpose times BA is equal to the identity matrix. That's our game plan here. So to start that proof, I'll do that in red. So these blue notes were just things to think about as we go through. So we're going to say let A and B be orthogonal matrices that's if you're likening this process back to high school geometry, this is sort of like the given. We're going to assume we have orthogonal matrices, and now we're going to use our setup here. We would like to massage out this BA transpose times BA. We don't know that it's equal to the identity yet, but this is what we want to tease out. We want to use matrix properties that we know about so that we can show that this indeed is equal to the identity. So first thing we want to do is apply matrix transpose properties back from chapter 2. Recall that if we have a product we're transposing, that is equal to the product of transposes, but the order switches. So this part here that I have underlined comes out as A transpose B transpose, and that's getting multiplied by BA. Because we assumed that A and B are orthogonal matrices, by theorem 6.9, B transpose times B equals the identity matrix. All right, so that again, that's by theorem 6. I think it was 9, right? Yeah, just want to double check the numbers. Theorem 6.9 part B. So that's why we made that little switch. If we have an orthogonal matrix, B transpose times B equals the identity. So we have that going on for us. Then we also know that multiplying a matrix by the identity matrix on the left results in the same matrix. So I can just change that to A. And then finally, again, I could do another application of theorem 6.9 part B. Now I have A transpose times A. We assume that A was orthogonal, so then the same result carries here. A transpose times A equals the identity matrix. So we can conclude by saying BA transpose times BA equals the identity matrix. So BA is orthogonal. And again, this is a result of theorem 6.9, part B. So that's all we have for this lesson. I hope that this was helpful, and I look forward to practicing with you more in class. See you soon.